All right, guys. We're gonna deal with complex numbers and the trigonometry that's incorporated with the complex numbers to understand essentially the complex plane. Okay. Um, this is one of the places where we have enough, I think, math background and a strong enough foundation to understand maybe the benefit of polar coordinates. Okay, and we're gonna take complex numbers, which using in rectangular form might carry with it in regards to some operations a very long process. But if we convert it into polar form, that process and the time involved is condensed dramatically. Okay, so kind of show you, I think a beneficial math idea to where why do we do some of the things that we do in math? Why is this interesting to us? And it's because it has application in being a process that creates efficiency for us. Okay, and can do very large calculations very quickly. Okay, so that's a really nice thing, especially technologically speaking. It's a very nice thing for us to have. Complex numbers are simply the real numbers with adding on I, right? Okay, it's the real numbers with the addition of that I component, and then being able to put that on essentially any real number. Okay, so when we talk about the complex numbers, we've been talking about anything of the form A plus BI, right? Okay, A plus BI. Okay, where A comes from your real numbers, and B is a component that comes from your complex numbers. Okay. Now there's a lot of things that we could talk about in regards to these things. The fact that 5 is a complex number, okay, but it doesn't have an imaginary component with it, right? 5 plus 0i would be that imaginary component. Therefore, 5 is a complex number. It's like saying that the number 4 is a rational number, even though we don't write it as a fraction, right? Okay, but it can be written as 4/1. So any number that we ever come across is a member of the complex plane or the complex number system. Okay, whether it has an I or not on it. The I is just an identifier for an imaginary component. Okay, representing a negative square root. Correct. Square root of -1 is what I is equal to. But we've done some work here. We've done things like A plus BI plus maybe C plus DI. You remember how we add these things together? Maybe if I gave you a specific example, 2 plus 3i plus maybe 6 plus 4i, how would you add those together? Yeah, you add the real numbers, 2 and 6, so it gives you 8, right? And then you add the imaginary components, so that gives you 7i. Okay? So in generic form, you took the real parts, A and C, you add them together. You took the imaginary components, BI and DI, and you added their coefficients together, right? So B plus D. So that's kind of the rule that we've talked about in the past with addition. Subtraction, same thing, except for now you subtract, right? Do you guys remember doing like an A plus BI times C plus DI, what that's going to look like? If I go 2 plus 3i times 6 plus 4i, remember how to do that? It's a binomial times a binomial, so you got to do what? FOIL. So 2 times 6 is 12. 2 times 4 is 8, and we've got the I there. 3 times 6 is 18, so we got the I there as well. And now 3i times 4i gives me 12I squared. But what's that I squared turn into? Yeah, I squared is, by definition, equal to -1. So now we've got actually a minus 12 here, right? So we get 12 minus 12. So it gives me 0. And then 8 plus 18I gives me 26I, right? Okay. So by rule here, that turns into, it was A times C, so AC. I don't need the parenthesis. AC. And we took A times DI. And we took BI times C. And then we took BI times DI. Okay, so plus BDI squared. But that all turns into, if you think about it, AC. That becomes a real number, right? Doesn't this become a real number? And we subtract, right? Because that I squared becomes a negative. So it'd be minus BD. And then plus, we add the AD and the BC together. AD plus BC. And then multiply that times I. So that's kind of the rule. If you wanted to apply kind of a quick way, instead of having to FOIL every time, just look at your components A and C, multiply them together, like components B and D, multiply them together, subtract that, and do the same thing with AD and BC. I'm not saying you need to know that, but it might be something that down the road at some point in your math careers that might be useful. Okay, but we remember doing that stuff, right? Hopefully we did that at the beginning of the year in college algebra. We did it. There's a complex component to algebra 2 that you should have done that with when you're dealing with quadratics, all that kind of stuff. So we're going to need to know that kind of fundamental adding and multiplying. We'll talk about division later on. But the reason we need this stuff, and it's mostly the multiplication right now, is that, if I wanted like 2 plus 3i, and I wanted to square that, that's going to look like this, right? 2 plus 3i times 2 plus 3i, right? But if I wanted to, and then I'd FOIL that one time. But if I want to go like 2 plus 3i cubed, we go 2 plus 3i, 2 plus 3i, 2 plus 3i. And we'd have to FOIL that one time, right? Get essentially another binomial. And then you have to FOIL that a second time to get my final answer, right? Okay. So there's some foiling involved. There's some messy foiling. What if I wanted to go 2 plus 3i to the fourth? Obviously, 2 plus 3i, 2 plus 3i, 2 plus 3i. Now, this is actually probably going to be a little bit less foiling than before, because if I FOIL those two, does that automatically FOIL those two for me? It gives me a binomial times a binomial. So there again, I only got to FOIL total without redundancy probably twice. Okay. But what happens if I want to do like 14, power of 14? Would you want to have to write that out, FOIL that, and do all that multiplication? No. Okay. Now you can use kind of shortcuts like we did in that one, where if I go 14, so I'll have basically 7 replications of 2 plus 3i times 2 plus 3i, and then I would have 7 binomials here to multiply together. And like I said, I could almost multiply 2 of them together, and that will then tell me how essentially groupings of 2 more work can look like. But I can keep doing that, and maybe using those rules to FOIL. Maybe I got to FOIL it out like 5 times. Okay, it's still a pain in the butt. It's still time consuming. Okay, still allows for us to make a lot of mistakes. Okay, working with a thing called De Moivre's theorem. De Moivre, his name is Abraham De Moivre, is a French guy, lived in the 1600s. He kind of bridged the complex plane and trigonometry. Okay, and his theorem basically says that if I want to take 2 plus 3i raised to the 14th power for some reason, okay, we can do that really, really quickly using trigonometry. And it comes down to us being able to do that by changing 2 plus 3i, which is in rectangular form, change it to polar, running it through a procedure that's very quick, okay, and then changing that back into rectangular. And it is the same thing as taking 2 plus 3i raised to the 14th power. So that's kind of where we're going to try to get to by the end of the period today. Okay, we'll try to get through all the stuff that's going to lead us into tomorrow. Our discussion should start with what the Moyer's theorem is. Okay, but we need some kind of foundational terminology, notation, that kind of stuff to get there. All right. First thing is graphing complex numbers. This is something we've never done before. Okay. If you remember back there working with quadratics in college algebra or algebra 2, when we had an imaginary component to our solutions or to our roots, we just said, oh, we can't graph that. Okay. And we couldn't graph that because our x-axis is all real numbers and our y-axis is all real numbers. There are no imaginary components to that, right? So in regards to wanting to graph graph the complex numbers, the way we end up doing that is we leave the x-axis alone. Okay, so this is still our x-axis. We're going to refer to it, though, as a values, and they are elements of our real numbers. Okay, so everything on that, what we called the x-axis in the past, it's still the x-axis, and it's still all our real numbers. Any number you can imagine is on there. Okay, your y-axis now, we now refer to these as b values, where that b value comes from our complex numbers. Okay, or actually, let's write it this way. Let's just say b is an element of the imaginaries. Okay. So your y-axis is removed and replaced with what we call our imaginary axis. Okay. And now that is the complex point. It is very similar looking to the xy point, right? The Cartesian. Okay. This is what we call the complex point. In the complex plane, every single number that you can imagine has a position. Okay, whether it has an eye on it or not. Okay, you know, all your real numbers are going to be on that horizontal axis. All your pure imaginary numbers are going to be on that vertical axis, and then anything like 2 plus 3i is going to be in one of the quadrants. Okay, so everything has a location or a position. So how do I graph an a plus bi? And this is the way you go about doing that. If I have an a plus bi, okay, right now we are referring to this as a rectangular form. Okay, stop it. So this is a rectangular form. So what we're going to do is we're always going to start at 0, 0 again. Okay? And that tells you how much to move on your real axis. So I'm going to move over a unit. So maybe a is right there. Okay? And then this tells me how much to move in my imaginary axis. So I'm going to move maybe b is right there. So I would move up b units, and I put a point right there. In that point, we're actually going to call it z and then put a subscript of 1, and that is the point a plus bi. And did we move in rectangular fashion? Yeah, we moved horizontally and vertically, right? So that's why it's called a rectangular form or rectangular system. We use the letter Z just for notation to say that we are working with complex numbers here. Okay, so instead of calling it like capital A or capital B or capital C like we do with ordered pairs that are purely real, the notation is usually Z sub 1, Z sub 2, Z sub 3, and so forth. Is that okay? All right, so that's how we plot imaginary or complex numbers. So if I want to take, let's say that 2 plus 3i, and I wanted to plot that, You see how we go from 0, 0, we moved to the right 2, and we moved up 3, and that gave us Z1. Okay? If I want to plot, let's go 2 minus 3i. 2 minus 3i, and you see as I move, that gives me Z sub 2 as 2 minus 3i, right? Here's a question to you. How are these two things related to one another? Conjugates. Okay? If, and this is just notation, if Z is equal to 2 plus 3i, then Z bar is equal to minus 3i. Z bar is notation to identify Z's conjugate. Okay. If I know Z is 2 plus 3i, it's a lot easier to say Z bar instead of saying that Z sub 2 is equal to 2 minus 3i. Just condenses our amount of kind of notation and writing. Some textbooks will use Z bar. Some I've seen like the Z and then an asterisk after it. Okay. Just understand whatever text you're using or reading, or maybe a PDF offline that I've given you or you found. You got to kind of understand the notation that author is using. Those two things are common. And WebAssign will ask you a few questions about Z and Z bar and the relationships. If I wanted to take 2 plus 3i and add to it 4 plus 5i, okay, and this is going off of what we've already talked about at the beginning of the class. That is two complex numbers, right? So I'm going to take the 2 and the 4, add those, and that should give me what? 6, and the 3 and the 5 should give me 8. So let's see if this thing goes to 6 plus 8i. And you see there, over 6, and then up 8, right? Okay. So whenever they ask you to maybe find, maybe, it's not the ones I've used here, maybe Z1 plus Z2 and graph that. That's all they're asking you to do is add the two complex numbers together and then graph that product. Or sorry, graph that sum. Okay, or what you produce. Does that make sense? All right, so that's nice. That's just the way that we graph things in the complex plane. If you scroll through these PowerPoints, you can kind of see that broken down, see similar examples. All right, so the kind of the bridge that allows us to kind of start talking about trigonometry and to allow us to eventually take these rectangular form complex numbers and change them into a polar complex number is this idea here. If I take any point, let's just say I'm taking Z1 here, and from 0, 0, I draw that vector. Okay. I know we haven't talked too much about vectors. It's just a line segment, a directed line segment. Don't really worry too much more about that. And this is a lot of times actually when they ask you to start plotting every once in a while, textbooks will say that when I plot Z sub 1, I need that line segment to be a component. Some textbooks just plot the point. Okay. A lot of times the graph of complex numbers is referred to as an Argand diagram. If you ever hear that, basically all they're saying is plot in the complex plane, and when you're done, make sure you got a line going from 0, 0 to that point. Okay, and the reason we want that line there is because we should have that segment there and that segment there that were the rectangular movements, right? This distance here was some A amount. This distance here was some B amount that was relatable to the A plus BI, right? If I want to find this dotted, or sorry, this orange line here, can't I take A squared plus B squared and take the square root of that? Does that make sense? Okay. What am I using there? Pythagorean theorem, right? Okay. Now, we call this thing Z, and we put the absolute value bars around it, so we call it the absolute value of Z, which it should be a positive distance. It's a hypotenuse of a right triangle, or if you want to think about it, it's a radius of some circle, so it should be positive every time that no matter what quadrant we look at it in. But we call that the absolute value of Z. And maybe you've seen this in physics when you guys talked about vectors. We have a word for this, and we call it the modulus of Z. And ultimately, just right now, means the distance of Z, or the length of Z for us, okay? Maybe you guys in physics call it the magnitude, right? Have you heard these words before? Okay, so there's some head shaking yes, some shaking no, and some saying like I have no clue what you're talking about. But these are just kind of they're terminology things that we have to kind of pick up on so we can work through the rest of de Moivre's theorem eventually. Okay, so modulus of Z is that length of Z. Okay, is that doable? All right, so let's kind of talk then about how this, or types of questions I guess you're going to see with the modulus. Okay. They might do it a couple different ways in regards to notation. They might say if Z equals 3 plus 4i, then find the modulus of Z, or like you're seeing here, they might just put Z and replace it with 3 plus 4i and write it that way. Does that kind of make sense? Okay. What you're seeing here, if it's 3 plus 4i, all I do is I take off the A part, I square it, take off the B part, square it, Pythagorean theorem, add them together, take square root, gives me 5. Okay? And that's directly related to, go back to GeoGebra, let's make this one, was it 3 plus 4i? 3 plus 4i. Move that thing over. Okay. So this would have been, so I write 3 plus 4i. 3. All right, so square that, I get 9, right? Square that, I get 16. That means then from A to Z sub 1 should be 5. Okay, so 3 plus 4i tells me the length of this thing here ends up being 5. Do the same thing here with this one. 8 minus 5i. Square the 8, 64. Square the 5, 25. Add those, you get 89. 89 is prime, so square root 89. And that would be the modulus of that complex number. Is it okay? It's pretty easy so far. All right, so how does that help us? Okay, so those are the preliminary things, facts, terminology that we got to talk about. So we can actually do this. We're going to take polar form of complex numbers. Okay? What I want you to understand is they're still complex numbers. Whether they're in rectangular form or the polar form, they're still complex numbers. Okay? Don't confuse that we're doing something and taking a complex number and changing it to a non-complex number. It's still the same number, just in a different format. Okay. So the idea is if I let a plus bi be a complex number in the complex plane, then I take that modulus z, that line segment or that vector, and that is the hypotenuse of that right triangle. It's the radius of some circle, and that's, you're thinking about polar. Polar, we're talking about circles, right? So we're gonna now say that, and you see it down here, that our r value or our radius is the same thing as the modulus of z, which we just figured out by the Pythagorean theorem, right? Okay, so those are just notation things again, just equating and talking about the same thing in different forms. Okay, so r is the same thing as the modulus of z. And if you think about this, guys, the way we've done this, okay, we've got our real axes here, and we zoom in. We've got our real axes, and we've got our imaginary axes. A lot of times they use r lowercase e instead of just the cursive r if they don't have the font to do the cursive r. Let's just say that we're back into x and y's. This was x, and that was y. Wouldn't this right here, didn't we say that was x is equal to r cosine theta? And if we're back in x's and y's, didn't we say that this here, this y, was r sine of theta? Where theta was this angle right there, correct? Okay. Well, the only thing that we have done here from the real plane, the Cartesian plane, to the complex plane is really a relabeling of the y-axis, right? And we're using b's instead of b's instead of y's, okay? And the relabeling of the x-axis, and now we're using a's instead of x's, right? So does it make sense that a, whatever this length here is, out to a, that length has got to be r cosine theta? And if this length here, this vertical length, which is relatable to that b, is the same thing as r sine theta? Does that make sense to everybody? Okay. And if you look at that right triangle, that should make sense. We know that that's A and that's B. Going through SOHCAHTOA, we could say that the sine of theta is equal to opposite B over R, opposite over hypotenuse. Multiply both sides by R to get R sine theta is equal to by B, and that's that right there. I can do the same thing for A down here. All right, so that tells us that all the work that we have done so far with rectangular coordinates in the real coordinate system, all that work kind of parallels to the work that we're going to do in a complex system. Okay. If we start with a complex number that is in the form of a plus bi, okay? So we're going to start with something that looks like this, a plus bi. That's rectangular. Okay? Well, we now know that the trigonometry shows us that A can be rewritten as r cosine theta, right? Okay, so let me do this. Z is equal to a plus bi. That's rectangular form. A is r cosine theta, so we replace that here. So we get that right there. Your B is r sine theta, so replace that B with r sine theta right there. Okay? But I can't replace the I, so that's why that I is right there. Okay? It still needs to be attached to the B component, which is now rewritten as r sine theta. Does that make sense? Okay. Now there's a couple different ways that we're going to write this. Okay. So this here, this is polar form of a
number. Okay? You have three formats. These are two of them. We go r cosine theta plus I times r sine theta. Okay? You also have the ability, since they both have r in them, to factor that r out. And this is one of the ways that WebAssign is going to kind of predominantly ask you to type your answer in. You've got r factored out, and then cosine theta plus I sine theta. Okay. And the last one, which is one that is actually, it's more concise, a lot easier to write, but a lot of times in mathematics, when we make things more concise in regards to notation, sometimes it loses meaning. Okay. And then the work that you have to do is kind of understand what's going on. So there's a payoff of, yes, it's less to write. There's a cost that, yes, now I got to know more, right? Does that make sense? And the way we write this final notation is the one that I'm going to use predominantly, because I think it's logical to do that. You take the R, you write R, and then it just becomes kind of like an acronym. C, take your I, and then your S. And you put theta at the end. Okay? And we read that R cis theta. Okay? And when I'm saying cis, no, I'm not talking about Magoo. Okay?
So r cis theta. And the vagueness of that one is that people forget that the cosine needs to have theta on it. The C, or kind of full, when I expand this, that cosine needs that theta as well. And the I and the sine go together. Okay? And then the sine needs the theta as well. Does that make sense? Okay? So those are the three types of notations that you see of polar form for a complex number. Theta, how do I find theta? Well, let's think about this. If I'm looking at some point up here, z equaling a plus bi. And there's a, there's b, the right triangle, there is theta. How do I find theta based off of b and a? Yeah. Theta, again, is going to be tangent inverse. If you go back to when we worked with the real plane, it was y over x, right? Well, y is now your b value, and x is now your a value. So it's tangent inverse of b over a. And a lot of times, theta is referred to as the argument of z. Okay? So in regards to putting something in, taking a rectangular imaginary number and putting it, a rectangular complex number, and it could be purely imaginary at some point, and putting it into polar form of a complex number, you need the modulus of z, and you need the argument of z. The modulus just meaning that r value, that distance, that hypotenuse, or the radius of the circle, and then your argument is just theta. Is that okay? Or the angle that's generated. So let's do a couple examples. And we're going to focus right now on really just going from rectangular to polar. Okay? Because if I want to reverse the order, you're actually going to see us doing this as we check ourselves. But reversing the order, going from polar to rectangular is really easy. It's just evaluating and knowing what your unit circle is. Okay? So it's just kind of natural to go from polar to rectangular. So we're going to do a couple of these examples. Do 1 plus I first. I think, guys, the safest thing for you to do, especially because we're going to probably grab our calculator here and ask our calculator to find theta for us, is to have a rough sketch of what's going on here with these points. So that you get the right, because remember when I use tangent inverse, my calculator is only going to give me numbers between negative 90 and positive 90, or negative pi over 2 and positive pi over 2. But if my complex number is in the second or third quadrant, I got to do a little bit of arithmetic to mess around with that. Or even if it's in the fourth quadrant, I got to mess around with it. Okay? So your calculator is going to give you insight. It's not going to give you the exact answer that you need, though. All right, so write each complex number in the form, or in polar form. So 1 plus I. So there's 1, and maybe there's 1I. So Z would be right there. Called Z1. Okay, that's 1 plus I. We're going to draw in that thing right there. Draw in that radius. Okay, so again, that's R, which is the absolute value of Z, or the modulus of Z, which is going to be found by taking the square root of A squared plus B squared, right? Okay, so right now the 1 is A, and the 1I, the 1 on that is B as well, right? So I'm trying to find R. Right this way. R is the same thing as the modulus of Z, which is the same thing as the square root of A squared plus B squared. And for us in this particular problem, it's 1 squared plus 1 squared, which is radical 2. Okay? So there is your modulus. Okay? Theta is looking at this angle right here. Okay? And theta is going to be found by taking tangent inverse of your B value divided by your A value, your complex coefficient, your imaginary coefficient divided by your real. And what would that look like, tangent inverse of 1 over 1, right? Which is just 1. What angle will give me a tangent value of 1? 45. Okay? Just pay attention to how they want their answers, whether they want in degrees or radians. Obviously, radians is more natural, but we're probably more comfortable with degrees still at this moment. Okay? But that is your argument. Okay? So now, writing our answer, we've got those components. Z in polar form is R cis theta. R was radical 2. I write cis, and then I put theta. And that is the polar form for that complex number. Now, you've got other ways of writing it. Okay, we kind of talked about that. So let's see if we can come up with those other ways. If we expand this, okay, what it means to us is that we got radical 2, and then the C stands for what? Cosine. And we need that argument. It's always then plus, and now I, the S stands for sine, and then we need our argument. That is an alternative way of writing it. Okay? If you want to oh, what did I forget? I forgot my radical 2 here. The R needs to go to the cosine, and it needs to go to the sine, so my apologies. I radical 2 sine of 45. And that's the thing that's the vagueness that's lost or created, I guess, when we condense the notation. Now, those two things, either one of those is acceptable. I think WebAssign a lot of times, it'll probably accept this, but a lot of times, if you get a question wrong and it gives you the answer, it's going to give you the answer this way. It factors out the R, and then writes cosine 45 plus I sine of 45. They write that way. Either one of those is fine. But I want to show you why this is, or how we know this is analogous to 1 plus I. How they're the same thing. One's just rectangular and one's just polar. Okay? And this is what you would do if they would ever ask you to go from polar to rectangular. Can you evaluate this thing right there from the unit circle? What is the cosine of 45? Root 2 over 2. So that's cosine of 45, and you've got this root 2 out front, right? Then you've got your I, You got root 2, and now what's sine of 45? Root 2 over 2. What's root 2 over 2? Sorry, root 2 over 2 times root 2? Yeah, that product up top is going to give me 2. 2 divided by 2 gives me 1. Same thing over here. Root 2 times root 2 is 2. 2 divided by 2 is 1. So that all right there goes to 1. And don't I have the I out in front? Is that the same thing we started with? Okay. So it's proof or evidence that we have the correct radical 2 cis 45, the correct polar form. Now, why is that beneficial? Because, like I said earlier, and this is what de Moivre's theorem is going to be, or help us with. If I take 1 plus 1i, raise it to the 12th power, that is very time-consuming. But if I take root 2 cis 45 to the 12th power, you can do that in about 15 seconds. Okay? And that's what de Moivre's theorem is going to get at tomorrow. So the benefit of being able to go from rectangular to polar is when I want to take something and raise it to a very high power. Okay? Or even square or cube it, I guess. It doesn't really matter how high that power is. It's a much more efficient process. One thing I want to do is kind of discuss this second one here quickly with you because of the location of it. If I go -1 plus root 3i, so -1 might be there. Root 3 is 1.7, so maybe root 3i is there. So there is z equaling -1 plus root 3 times I, right? Okay, so R is going to be found by taking your a squared plus b squared underneath the square root, right? So a is -1, b is root 3, and what's that turn out to give you? Yeah, root 4, which is 2. So that's your modulus. Okay. Theta, guys, theta is that thing right there. It's always from standard position. If I take on my calculator, root 3 and -1, if I say theta is equal to tangent inverse of opposite over adjacent, I get tangent inverse of negative root 3, which that gives me negative 60 degrees, doesn't it? Well, negative 60 degrees is not this theta, is it? But 60, the positive version of 60 would be that thing, wouldn't it? So how big would be the theta that I'm interested in be? 120. That's your argument. So then in polar form, Z is going to be R cis theta. So 2 cis 120. If I expand that, it's 2 cosine 120 plus 2i sine of 120. You guys agree with that? Can somebody tell me what the cosine of 120 is? -1/2. What's the sine of 120? Root 3 over 2. What's 2 times -1/2? -1. Those 2's cancel, don't they? You get I radical 3. Is that what we started with? So that tells me that this indeed was the right way of writing that complex number in polar form. Okay. I have